Hi everyone! In this talk I will present our paper Geometric Rank of Tensors and Subrank of Matrix Multiplication. This talk is all about tensors, so let me start by explaining what a tensor is. We are all familiar with matrices as two-dimensional arrays of numbers. Tensors are simply three-dimensional arrays of numbers. These numbers will come from some field, for example the complex numbers. Equivalently, we can think of a tensor as a collection of matrices as shown in the picture. Tensors play a central role in computer science, mathematics, and physics. In algebraic complexity theory, they are used to study the complexity of matrix multiplication. In quantum information theory, tensors represent quantum states and are used to study entanglement. And in extremal combinatorics, tensors have been used to study problems like the capset problem and the sunflower problem. Motivated by all these problems, we introduce a new tensor parameter called the geometric rank. The geometric rank assigns to every tensor some non-negative integer. Several important notions of rank exist for tensors. For example, the tensor rank, the slice rank of tau, the subrank of Strassen, and the analytic rank introduced by Gauss and Wolf. Geometric rank, like all these existing notions, extends the classical notion of matrix rank to tensors. Geometric rank is the geometric counterpart to the aforementioned analytic rank. Analytic rank is only defined for tensors over finite fields, for example, the field of size 2. In this case, it assigns to the tensor in a natural way a sequence of 1s and -1s, and then measures the bias of this sequence. Geometric rank, on the other hand, is defined for tensors over any field. It assigns to the tensor a geometric object and then measures its dimension. Our definition of geometric rank was greatly inspired by the definition of analytic rank. As our main result on geometric rank, we prove basic properties and invariances. We develop tools to reason about and sometimes exactly compute the geometric rank. We show some intimate connections to the other important notions of ranks for tensors. And finally, we answer a question of Strassen from 1987 on the subrank of matrix multiplication. The subrank is some kind of dual notion to the more famous notion of tensor rank. To say a little bit more about applications, we think that geometric rank provides a new interesting route to prove upper bounds on the subrank of tensors. This is important in complexity theory in the context of fast matrix multiplication and recent barrier results. As a result of this, geometric rank can be used to prove upper bounds on the independence number of hypergraphs. This independence number plays a central role in combinatorics in the context of the capset problem and the sunflower problem. Now that we've covered this rough overview of connections and applications of geometric rank, it's time to give the definition. We start with a tensor T, whose slices we denote by M1, M2, etc. We think of these slices as n by n matrices. From these matrices, we construct a system of equations in the following way. We multiply M1 from the left by a vector of variables x1 up to xn, and from the right by another vector of variables y1 up to yn. This gives me the first equation. We do the same thing for the other matrices to obtain the other equations. In this way, we end up with n equations in 2 times n variables. Then we consider the set of all solutions to this system of equations, which we call V of t. Now the geometric rank of t is defined as the number of variables minus the dimension of the set of solutions V of t. That is, it equals 2 times n minus the dimension of the set of solutions. This is also called the codimension of V of t. The notion of dimension we use is the one from algebraic geometry. Intuitively, dimension measures the continuous degrees of freedom in your set. So a set consisting of a finite number of points has dimension 0, a curve naturally has dimension 1, and a union of 2 planes has dimension 2. The formal definition would read something like: the length of a maximal chain of irreducible subvarieties. We will not use the formal definition of dimension in this talk. Instead, we will use some computational intuition. The first point of intuition is that the dimension of a linear space equals the notion of dimension from linear algebra. So, for example, this plane simply has dimension 2, as we're used to. Next, the dimension of a finite union equals the maximum of the dimensions. So, for example, this union of two planes still has dimension 2. And finally, very naturally, the dimension does not increase under taking subsets. Now we are ready to look at our first example. We look at a 2 by 2 by 2 tensor whose two slices m1 and m2 are as shown in the picture. We construct from these slices the system of equations as in the definition of geometric rank. The system of equations reads x2y1 plus x1y2 equals 0 and x1y1 equals 0. It's not hard to see that we can write this set of solutions as a union of three linear spaces of dimension 2. For example, it's clear that if we set x1 to 0 and y1 to 0, then we already satisfy the system of equations. And this gives us one of the linear spaces of dimension 2 that sits inside the set of solutions. Using one of the computational intuition rules, we now know that the dimension of the set of solutions equals 2, and therefore the geometric rank of T equals the number of variables minus 2, which equals 2. Now is a good time to make a general, easy observation, namely that the geometric rank takes values between 0 and n. To see this, we look at this set of solutions to the system of equations as in the definition of geometric rank. We notice that by setting all the x variables to 0, we always satisfy all equations. And in that case, all the y variables are free. So our set of solutions contains a linear space of dimension n. Therefore, it follows from one of our computational intuition rules that the dimension of v of t is always at least n, and it's clear that the dimension of v of t is at most the number of variables, which is 2 times n. We conclude that the geometric rank of t, which is 2n minus the dimension of v of t, is between 0 and n. So far, we've relied on our computational intuition to compute the dimension, but it's not true that every solution set can be written as a union of linear spaces. For small tensors, computing geometric rank is very easy in practice. Recall that to compute the geometric rank, we need to compute the dimension of a set of solutions to a system of equations. Software like Macaulay 2 or Sage can very quickly do this for small tensors with built-in functions, with the code that's shown on the slide. We do not know what the computational complexity is of computing geometric rank, whereas it's known that computing the dimension of a general variety is NP-hard. It is not known whether computing the dimension of a set defined by a bilinear system of equations is NP-hard. Let's finish this first part of the talk by stating our first theorem. Recall that in the definition of geometric rank, we sliced our tensor in one direction, and we called these slices the mi. Of course, we could have sliced our tensor in one of the other two directions, and one should wonder whether using those slices gives the same notion of geometric rank. Our first theorem says that indeed, slicing the tensor in any different direction gives exactly the same notion of geometric rank. Analogous to the fundamental theorem of linear algebra, which says that row rank equals column rank, one could interpret this theorem as a fundamental theorem of multilinear algebra. The proof of theorem 1 relies on a theorem from algebraic geometry about the dimension of fibers of projections. This concludes the first part of the talk. So far, we've seen the definition of geometric rank, the first example, and the first result on geometric rank. Now comes part 2, which is about the main technical result, namely monotonicity. This drives all the applications of geometric rank. To explain this, let's start with something we all understand, namely Gaussian elimination. Given the green matrix, we can take linear combinations of the rows and the columns to obtain a diagonal matrix. These row and column operations we naturally encode by multiplying from the left and from the right with some matrices. Let's use this to define an order on matrices, which we call the Gaussian order. Given two matrices M and N, we say that M is bigger than N if there exists some matrix A and some matrix B, such that A times M times B equals N. In other words, M is bigger than N if by taking some linear combinations of the rows and columns of M, we obtain N. Going back to our Gaussian elimination example, it's clear that the green matrix is bigger than the blue matrix. If we think about this order a little bit longer, we see that the matrix rank completely determines the Gaussian order. Namely, M is bigger than N, if and only if the rank of M is at least the rank of N. The Gaussian order on matrices naturally generalizes to tensors. To do this, we simply replace the words rows and columns by slices. Given two tensors T and S, we say that T is bigger than S if, by taking some linear combinations of the slices of T, we obtain S. These linear combinations are encoded by three matrices in this case, since we have slices in three directions. The Gaussian order that we just defined appears in mathematics, physics, and computer science in the following way. To determine the complexity of matrix multiplication, our task is to figure out what is the smallest identity tensor that's larger than the so-called matrix multiplication tensor. We will define these tensors later on in the talk. One way of classifying quantum entanglement corresponds to studying which tensors are bigger than which tensors. Finally, in combinatorics, the three-uniform hypergraph independence number can be studied by looking at inequalities that have a tensor fitting the hypergraph on the left-hand side and an identity tensor on the right-hand side. The notion of fitting is similar as the one used in the definition of the Hamer's bound. As we mentioned before, matrix rank completely determines the Gaussian order on matrices in the sense that M is bigger than N if and only if the rank of M is bigger than the rank of N. For tensors, that level of complete understanding is out of reach. First of all, deciding whether S is bigger than T is an NP-hard problem. And second of all, this order is not total. So there cannot be a single function from tensors to the reals that determines this order. An important question then is to find monotones for the Gaussian order on tensors. A function f from tensors to the real numbers is called a monotone if whenever s is bigger than t, it holds that f of s is at least f of t. Monotones can be very useful because they give obstructions. Namely, if f of s is strictly smaller than f of t, then s cannot be larger than t. So we can think of monotones as some kind of lower bound methods in the sense of complexity theory. Our second theorem is that geometric rank is a monotone. So if s is bigger than t, then the geometric rank of s is at least the geometric rank of t. It's actually not hard to prove this theorem given theorem 1, which we stated earlier. This concludes the second part of the talk. We've seen the main technical result about monotonicity. Now it's time to talk about some applications, namely to the subrank of tensors and the independence number of hypergraphs. Let's define the subrank. Given the tensor T, the subrank Q of T is the size of the largest identity tensor that's smaller than T. Here by identity tensor, we mean a tensor that has ones on the main diagonal and zeros elsewhere. The notion of subrank was introduced by Strassen in 1987 and is central in the theory of fast matrix multiplication. Besides this, the subrank naturally leads to a Hamer's bound for hypergraphs, which we've mentioned before. Namely, the subrank is at least the independence number of any three-uniform hypergraph for which T fits. Please see our paper for more details. Geometric rank upper bounds the subrank. The proof of this follows almost directly from the monotonicity result that we mentioned earlier, and the fact that geometric rank of a diagonal tensor equals the size. In fact, geometric rank upper bounds the so-called border subrank of a tensor. The border subrank, denoted by Q bar, is the approximative version of the subrank. Whereas in the subrank, we're looking for the largest diagonal tensor that's smaller than t. In the border subrank, we are looking for the largest diagonal tensor that's approximately smaller than t. This is a relaxed notion, and therefore Q bar is at least Q. We prove that geometric rank is at least the border subrank by showing that geometric rank is a closed notion in the following sense. If we consider the set of all n by n by n tensors whose geometric rank is at most R, then this set is Zariski closed, which means that it's defined by a system of polynomial equations. Let us now discuss how geometric rank connects to the other notions of rank for tensors. We've seen already that geometric rank upper bounds the subrank. The notion of slice rank, introduced by Terence Tao in the context of the capset problem, is also an upper bound on the subrank. And we proved that our geometric rank sits in between the slice rank and the subrank. Next, there's the notion of analytic rank. This notion is only defined for tensors over finite fields. It was introduced by Gauss and Wolff, and Lovett showed that the analytic rank is at most the slice rank up to a constant, and he essentially showed that the analytic rank upper bounds the subrank. So geometric rank and analytic rank compete with each other to give good upper bounds on the subrank. The geometric rank is defined over all fields, analytic rank is only defined for tensors over finite fields. As one of our main results, we proved that geometric rank in some sense extends the analytic rank to characteristic 0. Namely, for any tensor t with integer coefficients, we proved that the geometric rank of t, interpreted as a tensor over the complex numbers, equals the lim_inf, when p goes to infinity, of the analytic rank of t with its coefficients taken modulo p. The proof of this uses several ingredients. First of all, we use the Langwey theorem, which provides good bounds on the number of fp points for nice varieties in terms of the dimension. Secondly, we use the Bertini-Noether theorem, which relates the fp dimension to the complex dimension of a variety. Finally, we use a generalized Schwarz-Sippel lemma, which provides a coarse bound on the number of fp points for all varieties. We now come to the final topic, an application of geometric rank to matrix multiplication tensors. The family of matrix multiplication tensors plays an important role in the complexity theory of matrix multiplication. The smallest matrix multiplication tensor, denoted by angle bracket open 2, 2, 2, angle bracket closed, is a 4 by 4 by 4 tensor. Each slice is a block matrix with one of the 2 by 2 blocks equal to an identity matrix and the other blocks equal to 0. The next matrix multiplication tensor, denoted by angle bracket open 3, 3, 3, angle bracket closed, is a 9 by 9 by 9 tensor, such that every slice is a 3 by 3 block matrix, such that one of the 3 by 3 blocks is an identity matrix and the other 3 by 3 blocks are 0. It is clear how this generalizes to larger dimensions. As a first simple application of the geometric rank, we compute the border subrank of all matrix multiplication tensors. Recall that the border subrank, denoted by Q bar, is the approximative version of the subrank. Our theorem says that the border subrank of the n matrix multiplication tensor equals the ceiling of 3/4 n squared. The lower bound in this equation was proved by Strassen in 1987. The upper bound is obtained by simply computing the geometric rank of the matrix multiplication tensors, and magically its value exactly matches Strassen's lower bound. In fact, we can also use geometric rank to compute the border subrank for rectangular matrix multiplication tensors. And again, the answer exactly matches the lower bound of Strassen. This concludes the third part of the talk. We have introduced a new notion of rank for tensors called geometric rank, which extends the notion of rank for matrices. And we've seen some results and some examples. I would like to finish by stating some open problems related to geometric rank. First question is, what is the computational complexity of geometric rank? It is known, for example, that slice rank is NP-hard to compute, and we may expect that geometric rank is also NP-hard. For the second problem, recall that geometric rank is at most slice rank. But how much smaller than the slice rank can the geometric rank be? We don't know. The analogous question for slice rank and analytic rank is actually a big open problem, and several papers have appeared recently proving a polynomial relation between the two notions. For the third problem, recall that we proved that the geometric rank is the lim-inf of a sequence of analytic ranks. Is it true that geometric rank is in fact the limit of analytic ranks? This concludes the talk. Thanks for your attention. Feel free to send us a message if there are any questions.